to introduce what are the issues and approaches and how we have addressed this problem in our research. So that is the agenda for today. So before I start my talk, I would like to thank Dr. Prasanna Venkateswaran and Dr. Vinod from NIT TRICHY for extending the invitation to me to give this talk. Dr. Varun Jain, he was my PhD student, and he is the person who worked with me for this patient scheduling problem. Most of the work I'm going to present today is predominantly what he did for his PhD work. Dr. Zach Zakaria and Dr. Nada Sanders, they also actually collaborated with us on one of the research projects. A lot of clinics and hospitals which provided crucial data for our research. And finally, I would like to thank AICTE Training and Learning Academy for this program and for giving me this opportunity. So what can you expect in the next 2 hours? More than focusing on the nitty-gritties, I thought that this talk, I will tell you as to what are the approaches from a researcher's angle and what are the research problems that are available in this patient scheduling problem. So that you can align yourself no matter from which area you come or what are your interests. I can tell you what are the type of problems that are being addressed here, and I will discuss about 2 of the problems in slightly more detail. Given the time constraint, I will not have time to deep dive into anything. I'm sure that you all can go back and refer to your own since this is a very learned audience, I'm not going to go into the nitty-gritties, but however, I'll give you an overview of these problems so that you can go back and pursue this if you are interested in. So let me share the agenda. So I'll start briefly with introducing the problem. I will give you a overview or the literature review as to how healthcare and operations is generally handled. And then afterwards, I'm going to focus on 2 key modeling perspectives. One is modeling healthcare scheduling problem as a shop floor scheduling problem. Now, many of you who are from industrial engineering or who come from a manufacturing background, especially people who are from mechanical background or IE background, you would be able to relate to a shop floor scheduling very immediately. This purpose of this module, that is shop floor scheduling in healthcare, is to introduce you to the concepts that are borrowed from shop floor scheduling, like flow shop, open shop, hybrid shop, and apply it to the healthcare settings. That is the main idea of shop floor scheduling. And then the next procedure or the next model we are going to focus on is what we refer to as a mark-out decision process model. So these are 2 very popular modeling technologies or modeling frameworks that are available when we talk about patient scheduling. I will talk about these 2 and give you 2 examples one from shop floor scheduling and one using MDP. This is the overall structure. And I'll also briefly introduce you for those who come with an ML or machine learning background, how reinforcement learning methods can actually help you in this area. At any point of time, if there is a doubt, Dr. Prasanna, they can use the chat box.
Yes, madam, I enabled the chat box for them. They can raise their doubt. Yeah.
Okay, you can please stop me because I don't want it to be one way. If there is any question or any problem, you can please use the chat box and I'd be happy to answer. Now let's move and start the session. Most of us are aware of cues of this kind. Yeah. So you can even unmute can they unmute themselves? Or only the chat box?
No, they can unmute. They can unmute.
Yeah. So what can you see here? The picture that you can see on your screen. Anyone?
Patients are in the queue, madam.
Patients are in the queue. And how many of us are actually experience this kind of a situation?
For me also, I have admitted my father in hospital, madam.
Yeah. So all of us and what, yeah. Yes, please
for
proceed.
purchasing for purchasing medicines, for purchasing admit card, for each and everything, I have stand in line, madam.
You stand in a line. And if you're an operations person, did you ever think that you could improve or reduce the wait time?
Yes, madam.
Right. So that is our whole idea, or the whole purpose of this talk is to try and see whether we can come up with more effective and efficient ways of scheduling patients. And this is just something which each one of us are experiencing on a day-to-day basis. Be it you're an outpatient or be it you're an inpatient, the average time taken in any hospital from the time the doctor says that a patient can be discharged to actual time of discharge is anywhere between 3 to 6 hours, depending on whether the patient is an insurance patient or not an insurance patient. So you see that most of our healthcare delivery systems are operating at these levels of what we refer to as inefficiencies. So when we look around and we say that these are the levels of inefficiencies, you look around as a hospital. So I can look at this hospital as a complex system where I have players which are doctors, nurses, technical staff. It has many facilities and all of them have to work in perfect synchronization for an effective healthcare delivery. One of the places where we see lot of queues and inefficiencies manifesting is what we refer to as the outpatient center. Now, even in an outpatient center, there is a high dependency on resources. And particularly in India, we have a constraint on resources, be it consulting doctors, be it equipment, be it wards, be it administrative staff, be it ambulances. We are severely constrained in each of these resources. You walk into any hospital, you find all of them are crowded, be it a general hospital or be it a private hospital. So you see that there is a very emergent need or very significant need for us to actually come up with an efficient operational model. Though we are not aiming to solve the entire healthcare delivery system model, our purpose here is to see where we can make a difference. And that's what we are going to talk today. So when I talk about healthcare delivery systems, the one thing we need to understand is we face enormous pressure about managing scarce resources. Now, what do I mean by scarce resources? You can see that not all hospitals have what we call MRI. Not all hospitals have what we call as CT scanners. Not all hospitals have X-ray. And even if they have a CT scanner or an X-ray, you see that a lot of patients compete for the utilization of that resource. So when you look from a challenge these healthcare delivery systems face, they need to serve the patients. Now, when they need to serve the patients, they want to come up with efficient ways of serving the patients without having to keep them waiting. One immediate thing is, okay, let me increase my resources. But the minute you look at the resources, be it an MRI scanner or be it a CT scanner, you know that these are all capital intensive. So the answer that, okay, buy another resource does not work most of the time. So the question here is with the available resources. So I am severely constrained with my resources. So with the available resources, how best can I or what best can I achieve in keeping the patients happy? So we need to borrow our ideas from operations research. Because when I'm looking at operations research is always about achieving trade-offs. What are the key trade-offs I want to do? I want to minimize patient time and I want to maximize resource utilization. Minimize patient time is from a patient perspective. Maximize resource utilization is from the health delivery or the health delivery system perspective. So this trade-off or this matching expectations of my customer. Customer is the patient and the service provider is the healthcare delivery. That trade-off, how best can I achieve? And we are going to see how OR can help us achieve this problem. So again, as I mentioned, there are going to be three key themes I'm going to address today. One is how this can be addressed by modeling the problem as a shop floor scheduling problem. The other is how do I model it as a mark out decision process. And finally, keeping in times, how can this be looked at some machine learning and how can reinforcement learning models work? Now, before I go, I just want to present a few books which could be of interest for researchers or faculty in this. The first book which I have here, which is the Operations Research and Healthcare book. This is a very good book. This is an edited handbook on product methods and applications. And this is for the entire healthcare. You have right from managing blood banks to managing routing of ambulances to policy, health policy to everything, how OR can work in each of these different dimensions. Whereas the second book by Brian Denton is a handbook on healthcare operations management. This looks at healthcare operations management, and it's not only OR model, it looks at OM models also. The third book talks about quantitative decision making in healthcare settings. So this is what they refer to as healthcare management engineering. The fourth book is again a handbook on healthcare delivery system. For the purpose of today's lecture, these two books are very, very crucial. The first book was a handbook on healthcare system scheduling. This is edited by Randolph Hall. And the second thing is on health operations management. In particular, it talks about patient flow, and it basically focuses on patient flow systems. So these are the popular books, and if you look at any paper that refers to patient scheduling, you'll find a reference to at least these books for sure. Now let's look at how the literature has evolved in this one. First, I said OR in healthcare. So this is a very good sort of reference, which is Rice and Vaina. This is in 2010. This is a review paper, and this review paper actually gave a complete review of all the OR models that are available in healthcare, and the framework they came in, they broadly classified it into healthcare planning, healthcare management and logistics, healthcare practices, and specialized and preventive healthcare. Within this healthcare management and logistic, you can see that this is what we are going to focus on, is what we are going to call patient scheduling. So typically in this bracket, you find a lot of models that are OR or operations research models. So in this paper, they actually reviewed critical optimization issues. And by optimization issues, we refer to service planning, resource scheduling, logistics, disease diagnostics, preventive care, everything. And another thing that they identified or they said in this paper was a commonly used tool is simulation. So this actually sets the mood for this entire workshop, which is data analytics and simulation for healthcare supply chain management. Without looking at healthcare supply chain management, if you just look at healthcare delivery, healthcare management and logistics, this paper has actually said that simulation is one of the most commonly used tools. When you look at simulation as a tool in healthcare, this paper by Jun et al. In Journal of OR Society in 1999 actually surveys the application of discrete event simulation models in healthcare clinics. Whereas a very more recent paper by Saleh et al. Is actually giving you a systematic review. In fact, it is a meta review of simulation modeling in healthcare. So for any one of you who hopes to deep dive into simulation and healthcare, you can refer to these two papers. You'll have a good understanding of how simulation as a tool is applied in healthcare both healthcare supply chain or healthcare delivery. Hulshoff and all in 2012, meanwhile, came up with what we refer to as a taxonomic classification of planning decisions. So when we look at planning, we always know that there are three levels of planning decision. One is at a strategic, this is a long-term, tactical, which is a medium-term, and operational, which is a short-term decision-making horizon. So within each of these planning decisions, we do have ambulatory services, emergency care services, surgical care, inpatient, home care, and residential care services. And you can see that patient scheduling occurs in one of the schedules. So this paper again is a very comprehensive review from the field of ORMS to come up with a taxonomic classification of planning decisions. Now, with respect to this talk, one of the review papers which is very close to patient scheduling is this review by Denton and Gupta. Denton and Gupta have reviewed the literature on what we refer to as healthcare appointment scheduling. Now, healthcare appointment scheduling is where patients are given appointments, or this is prior to the appointment scheduling. So they are discussing three environments. One is a primary care, specialty care, and elective surgery. And they actually further explain the complexities of the arrival, service, and patient and providers' preferences and incentive and performance. However, when you look at Indian setup, very rarely do appointments work. Most of the time, the queuing systems in India follow a first in, first out. Even if appointments are taken, we have visited several clinics and hospitals, and we have actually gathered data as to how these queues are formed. Even in clinics and hospitals where appointments are given, if a person without appointment takes a token prior to the person whose appointment is there, the person with the token always gets preference to meet the doctor. So appointments are rarely followed in this case. So when we looked at this problem and we saw that, okay, there is a very good research problem as a researcher's perspective, and from a social perspective also, you see that this healthcare delivery system or patient scheduling is a very, very important problem for us to address. So we further went and saw as what are the decision support tools that are available in outpatient appointment systems. We saw that this paper by Ahmadi Javed gives a comprehensive review of decision support tools from optimization models. So keeping all of this in consideration, we just wanted to understand, okay, how do we go about looking at our problem? So we looked at two possible healthcare systems. In the first healthcare system, this is where we looked at what is called a preventive healthcare system. How many of you are aware of preventive healthcare systems? By preventive healthcare system, I mean all these checkup plans, master health checkup plans. I'm sure all of us at some point of time or the other has been a patient or has been a client of these master health checkup plans. Would you agree with me? What do you think is the average time you would have spent if you have gone for a master health checkup?
Participants can unmute and you may please respond to madam.
Yeah.
3 hours, madam.
3 hours. Anybody who has spent more than 3 hours?
Depending upon number of tests, madam.
Yeah, depending on number of tests, it can be anything between 3 hours or 5 hours, right? So this is the first environment which we are seeing is what we call a preventive health checkup. And according to reports from Deloitte and etc., we see that this health checkup is just going to increase in the future. So you see that a lot of healthcare delivery systems, by healthcare delivery systems, I mean both hospitals and just exclusive healthcare delivery systems. For example, you have the medals and everything, which offer only preventive healthcare systems, come up with different plans. For example, you could have a senior women health checkup plan. You have a senior men health checkup plan, you have a platinum plan, you have a gold plan, you have a silver plan. So you have many plans, multiple categories of health checkup plans. In other words, I bundle different tests. For example, I could have a test which just has 3 or 4 tests and I call that a plan. Some for a particular woman, for example, come March, you'll find every health checkup which is competing by giving all discounts on women health checkup plans. All of you are aware of these things, right? Yeah. Now, what is the biggest challenge faced by such health checkup operators? You have multiple categories of people coming here, and the challenge that is faced by these people are, how do I schedule my patients? Can I reduce the 3 hours to 2 hours? Is it necessary for me, or is there a more efficient way I can schedule the patients and at the same time utilize my resources? So this is with this motivation, we thought that, okay, is there something I notice about this health checkup that I can model with whatever I have already seen? So let's go and look at the problem description. If I look at the problem description, you see that this whatever I have highlighted here is the typical thing. I enter, I get a test. From this test, I finish. So this could be my just blood test. After blood test, I might want to go for another, say, treadmill test. And I could either go to test 3 or test 4. If I finish test 4, I could go to test 3. If I finish test 3, I go to test 4 and then I exit. So what I notice here is test 1 and test 2 have to be done in sequence. Or I could have a test 3, test 4. This could be one sequence. I could have test 1, test 2, test 4, test 3. I could have another sequence. In other words, this is where I see that whether I can borrow from my shop scheduling literature and model this as a shop scheduling problem. Is this clear? The motivation to look at it as a shop floor scheduling problem? This sequencing of people in this testing, I'm going to look at it as a shop scheduling problem. Is this clear, please? Yeah.
Yes, ma'am.
I'm just going to just introduce a few definitions. I have already shared the slides, so I'm not going to go in detail. So when you look at shop floor scheduling, we already know what is scheduling and what is a flow shop. In a flow shop, each patient has to undergo a series of tests. And these tests have to be done in some order, in the same order, implying that the patients have to follow the same route. Okay, that is a flow shop. Now, in a job shop, the routes are this one, but not necessarily the same for each patient. Open shop, I could have the route of the patient is immaterial and it's up to the scheduler to decide. Hybrid shop is a combination of whether, suppose out of the first test, the first F test form a flow shop and the other form a open shop. So borrowing from this literature, and also what is a flexible shop, when I have multiple parallel resources to perform the same test, I am going to actually see that from a healthcare perspective, what is it I am interested in. So again, there are two performance metrics when I look at shop floor scheduling. They are flow time and make span. The total flow time is the time taken by all patients to finish the required number of tests, and make span is the time at which the last patient leaves the system after finishing all the tests. Now, using these two, I can say that the make span, a minimum make span usually implies a good utilization of the resources, and minimizing the total flow time is to enhance the service quality. So I am looking at, from a patient's perspective, I'm looking at minimizing flow time, and from a service provider's perspective, I'm looking at minimizing the make span. So using this, we define, and this is the paper that appeared in Operations Research for Healthcare. In this paper, basically, we are modeling this situation. And this situation is a preventive healthcare checkup situation. We have borrowed from the shop scheduling literature to model this preventive healthcare checkup. And we are, once we modeled it, that is, we come up with an MILP, mixed integer linear programming problem to model this kind of a situation. The next is solution. For solution, we have implemented what is called an online genetic algorithm. The reason why it is an online is we have somehow the arrival of a new patient. It is dynamic and real time. I can actually adjust my entire algorithm whenever a patient enters the things. That's why it is called a novel online real time scheduling algorithm. So what is this problem, the online scheduling algorithm? In this problem, what we are looking at is the following. I have a multi-facility diagnostic center with L tests. By L test, I could mean a blood test, I could have a treadmill, I could have a ultrasound scan, X-ray, mammogram, and not all of them need to have everything at the same time. Each test consists of MI identical parallel resources. Now, some small clinics do not have parallel resources. They might have only a single resources. But when you look at big hospitals, you might have more than one X-ray machine or more than one CT scanner. So if I have two CT scanners, this MI would be 2. So in that case, I am borrowing from the flexible shop literature. I have multiple patients. These are patients are the jobs belonging to U packages, which are again categories. They arrive at random. I have a predefined sequence for the first F test. So I have to have my blood test, which is the fasting blood test. That has to be my first test. So that's why I have a predefined. After the fasting blood test, I have to go to another test and I have a sequence. This is a predefined sequence. After the predefined sequence, there is no precedence for the next test. So the next tests are actually an open shop. So this is my problem, this one. And hence I have this entire patient scheduling problem posed as a flexible hybrid shop scheduling problem. Now in many things, I have a fasting blood sample and a postprandial blood sample. There is a time window that is fixed between these two blood samples, and that time window is fixed. My objective here as an OR problem is to minimize my total flow time and efficiently use the resources and minimize the make span. And for here, I'm looking at an online scheduling algorithm. I pose this as a, so what are the main assumptions I have here? The patient's category and test required by each category of patient is known. Service time is known. Arrival is independent. All resources should service one patient at a time. Priority level of all patient category is the same. I don't have any priorities that I have here. And I'm also looking at the service time that is known. So pretty much everything is deterministic in this model. So since everything is deterministic in this model, I go and I model it as an MILP problem. Now, if you can see what is being displayed on your screen, you can see that this modeling in the healthcare using a shop flow scheduling problem is not new. If you look at it, as early as Via et al. At 2011, they modeled it as a job shop scheduling problem. They formulated as a BIP and they used a variable neighborhood search method to solve the problem. You can see that all these problems which I have listed here have looked into the offline. That is, it was not an online environment. Most of it are either BIP and MILP, and the solution methodology have been variable neighborhood search methods or genetic algorithms. You can see all of these are genetic algorithms. The closest that comes to our work was by Azadeh. Azadeh actually has again formulated it as a hybrid shop flow problem. Again, it's an MILP. He gave a genetic algorithm with, again, in a semi online thing, and it's very close, where the objective was to look at the minimum total completion time of patients. In this paper, we have looked at the health checkup plans, where we want to minimize both the total completion time and minimize the make span. So this is both this is a flow shop and an open shop. Hence, it is a hybrid shop. And we look at it at a real-time online problem. So the major contribution of this work was we gave an online genetic algorithm and we scheduled it active. So this is what this paper does. I'm going to just look at the formulation here. I'll just give a brief of the formulation. These are the notation, and let's look at the formulation. As I said, my objective, I had two objectives, and the objective was to minimize both total completion time and minimize the make span. I have written both these objectives here, which is total flow time and make span. The first two, so this is so once I minimize these two, the first two constraints are the constraints which tell that the service should start after arrival of the patient. And the second constraint is a precedence constraint. I said that the first F tests are what I'm going to model as a flow shop. So in the flow shop, I have a sequence which I have to maintain, and those are what I maintain here. I also said that there is a time window between the postprandial breakfast and after finishing the breakfast test. That is what I have modeled in these two constraints, where I'm saying that the test F+1 will start only after my breakfast is over. So you can see that when you're going, you have a fasting blood sample and postprandial blood sample. That is what we have listed here as FBS and PBS. The next constraints are actually constraints to compute the flow time and compute the make span. And it's also this constraint ensures that a patient is allotted to only one resource to complete a test at any point of time. Finally, these constraints ensure that only one test of a patient is scheduled at a time. And because I have binary constraints, I'm having the linking constraints to complete my formulation. So this is a pretty straightforward formulation. We have a genetic algorithm to address this formulation. And in this, because MILP works for very small instances, we looked at an online genetic algorithm where we broke the problem again into two parts. The first was again a flexible flow shop scheduling problem, and the second was a flexible open shop scheduling problem. We use the response surface method for fine tuning the genetic algorithm parameters, and this is the overall high level diagram or the flow chart for the online genetic algorithm. In the interest of time, I'm not going to go through in detail. The reference for the paper is given and you can go through the paper. Now, once we implement the online genetic algorithm, we actually conducted two empirical studies. The first empirical study did not have any parallel resources. But as you can see that the number of tests in that first empirical study, I have the C1 is when a person comes into the system, then there is a fasting blood sample, then there's a breakfast, and then there is the echo, mammogram, pap smear, ECG. Not all patients go through everything. For example, some tests are only for some people. In that case, we have just taken the service time for that person in a particular test to be 0. The second empirical study was conducted at a larger hospital. In this, I have parallel resources. So the number on top of each of these resources indicate the number of parallel resources. So in my reception counter itself, I had 4 people or the 4 things which are in the reception counter. For the fasting blood sample, again, I had 4. For the treadmill, I had 3. Ultrasound, I had 3. X-ray, I had 2. So you can see ECG, I had 3. So everything I had a parallel resource. Now, what is the importance of this? When you look at the average float time, the average actual system, when we simulated the actual system based on the data we collected, the average float time was close to 60 hours. And when we scheduled it using the online genetic algorithm, it was brought down to 42 hours. Similarly, the make span from 2.8 hours was brought down to 2.65 hours. Whereas when in the with parallel resources also, you can see that the OGA did much better than the actual system. So the implementation of this genetic algorithm, actually, we can show the graphs that you can see on the screen shows that the OGA did very well in performance wise. Now, here so in conclusion, what we did in this paper was we proposed a bi-objective online genetic algorithm. The genetic algorithm, the fine tuning of the parameters was done by response surface methodology. And for both the centers, the proposed OGA showed significant improvement as compared to the simulation model. We came up with a lot of business insights based on this. According to the current practice, as the number of patients increase, the average time a patient spends in the system increases. So we saw that also so I have not presented that part here, but in the paper you can see that we found that as the number of patients increase, the average time also increases. So one thing that we also simulated and saw is there a way I can level out my appointments? What do I mean by that? We also noticed that these are preventive healthcare systems. The number of patients on a weekend was very, very high. And that is something which again puts a constraint on the system. So one way we thought we could level this out is, can we call people on a weekday, level it out by saying that, okay, if people come on a weekday, we could give discounts. So we are actually what we suggested was, why don't you incentivize people to come on a weekday? Obviously, people who are perhaps in jobs cannot come, but senior citizens, you can incentivize them to come on a weekday. Hence, by telling that you spend much lesser time if you come on a weekday. So we have used the results to come up with incentive plan. This was one of the insights that we drew. The second thing is, if you look at it, there is a 2-hour window between your fasting blood sample and your postprandial blood sample. What this does on the system is, all my patients arrive at the same time because the fasting blood sample has to be taken when you are fasting, or it should be on an empty stomach. Now, when every patient arrives at the same time, what would happen is your total float time would actually increase. So the one thing is, if there is a way to collect the fasting blood sample, and that is something which was implemented also. So now we have home collection services. Okay. For blood, you have a lot of home collection services. So if the home collection is done for your fasting blood sample, then 2 hours from that fasting blood sample is when you can start all your tests. So that again has a considerable reduction in the total time and improvement in the performance metric. The third thing was, how do I add more parallel resources? Because I see that adding parallel resources further reduces the time spent in the system for the same number of people. But here we need to do an economic analysis. Where if I have to add parallel resources, we are talking about adding capital intensive parallel resources. An MRI or a CT scanner or an X-ray are capitally intensive. Unless I'm able to convert whatever I'm going to have in this regard and show the trade-off that investing in a machine would result in getting more patients or serving more patients, it would not make sense for me to add more parallel resources. I need to do the economic analysis to take a decision on whether I should add more parallel resources. So in summary, what the first part of the problem I wanted to discuss was how something that has been existing in IE literature and a lot of models developed in IE literature, namely the shop floor scheduling, can be applied in healthcare settings, and how you can solve the problem and come up with efficient algorithms to solve the problem. This is the first part of my talk. I'd be happy to take any questions.
Participants, you have any questions? Maybe you can.
Yeah, please. We have about 5 minutes left. I'd be happy to take any kind of questions, please.
Do you have any questions there? Can you put your questions?
Madam, this case studies will be suitable for emergency case, madam.
No, see, this is basically the setup I have talked here is where, so if you go back to the assumptions, I assumed that there is no priority. Okay. The next case study or the next thing I'm going to talk about is where I have a priority.
Okay.
So this is the system. So basically you can, when can I model it in this way? When I have a sequence of tests that have to be performed, right? When I'm having the job shop or a flow shop model. Okay, that is when I can model it in this way. But when I'm not bumping off patients or I'm not having any priority here. The next thing I'm going to talk about, I'm going to bring in how I can introduce the priority customer also. Okay.
Okay. Okay.
Any other questions, please?
You have any questions there? Otherwise, shall we take a 10 minutes break and join for the session 2? Can someone respond?
Yes, sir.
Okay, thank you. Thank you.
Okay, right.
We'll
So I'll
start
join
then,
at
madam.
8. Yeah, 8 o'clock.
Yes, madam. Sure, madam.
Thank you. Yeah.